All right, so we'll go ahead and get started. Welcome, everyone. Again, we're really happy you could join us today for this presentation on process twins for decision support. We've got Dr. Diego Rosso and Dr. Nader Rezai from the University of California, Irvine, and their team to present on this today. A few logistics before we get started. Please note this meeting is being recorded, and like all of these webinar recordings, it will be posted to the NAWI Alliance community website after the event. We highly recommend you check that out. We've got a lot of great content in there to catch up on and view. So please make sure you check that out. Attendees are joined in listen-only mode. That means you will be muted throughout the presentation. That said, we very much do want your questions and comments, so please put those in the Q&A or chat box, and we will keep an eye on those and address those at the end of the webinar. If you have any audio issues in particular, a lot of times connecting through your phone for the audio can fix that problem. If you have any other technical issues, please send us a chat and we will help you work through those. Also, a reminder that we do offer cost share for your time spent during this webinar. We will put this link in the chat so you can fill that out. And if you have any questions about that cost share program or any other general NAWI questions, feel free to email us. And that's all for me. I will turn it over to Diego to get us started.
Hello, everyone. Good morning and good afternoon, wherever you are. And we have here the deck now that is pulling it up. So today it's my pleasure to introduce a team and introduce the slides on behalf of the team and then pass the baton to the rest of the team members to tell you the story about this project that is ongoing. And the project team here, you can see it's two institutions, UCI and Oak Ridge National Lab. And we have a number of people today here from the team who will present. Well, Philip Bingham is the co-PI with me managing the project. And then from Oak Ridge, we have Chris Villet, Alex Melling, and Sally Ganem, who are three researchers. From UCI, we have Brian Taroja, who's a researcher. We have Nader Rezai, who's a postdoc, and Puri Gorbani Bam, who's our PhD student. And before we go to the next slide, I wanted to point out in the banner on the bottom, we have a lot of logos. And yeah, we have our two institutions, but we have participating utilities, Orange County Water District, HRSD in Virginia, LA County Sanitation District, and also we have Brown and Calder and Glacier Technologies, who are from industry and who are supporting the project. And first of all, I want to say that Orange County Water District deserves all of our praises and many thanks and Nobel Prize for hosting a project and supporting it, because I can never find enough words to thank them for all the support they've been giving us in the field and to the rest of the team. They're hosting the pilot there. And also I want to acknowledge Glacier Technologies, who have been really generous with their support in helping us fabricate and commission and debug all the pilot unit. So in the next slide, we will see the outline of this talk. And the reason why I have an outline is because different speakers will cover different points. So I'll tell you about the premise of the project, the project rationale. And then Nader will go over the introduction to what are digital twins and how we get by developing them. And then the folks from the National Lab will tell you about the digital part, the digital twin, the connectivity, and the optimization problem and the modeling approach. And then we'll go back to Brian here at UCI. Will talk about energy and cost analysis. Energy is a very big component of this project. And then at the end, Chris will wrap up with the next steps before we'll entertain the Q&A. So why did we assemble this diverse team with highly complementary expertise to propose this project? Very often you go to conferences, you hear people about presenting digital twins, and most of the times it's consultants who deliver a product for their client. And here we're using the digital twin as a tool. We're not delivering a product and walking away. We want to develop something that we can use to answer some research questions. Some of the challenges to be addressed here are that, historically speaking, most water use plants are a patchwork of data collection and process control that tend to be developed and delivered by the manufacturers of the individual units. This is very different than the space of water reclamation, wastewater treatment that some of us come from, where everything tends to be designed as an overlay, soup to nuts. And this is more fragmented in water use and attached to the equipment. And very often the sensor is not placed or maintained in what we will say it's an optimal schedule or optimal location, optimal frequency. And in the water use space, a dynamic process-wide simulator that also includes the energy dynamics, it's until very recently didn't exist. And so we are using a commercial product, a simulator that exists in industry. It's called Sumo, and it's we are going to have some slides describing to you what it does. And the reason why we're using it is because all of these units are already available in this simulator, and it's editable, so we can use it for research. And throughout the course of the project, we also apply for one of those project enhancement grants, and with the WaterTap team. And we want to credit them for working with us. And to answer the question, when is the dynamic modeling part of individual unit or the whole process necessary? So we have to move from steady state to dynamic modeling. And then that's the part that later will be discussed and presented about the joint work with them. So a few research questions you see there to pitch your interest in the rest of the presentation. First one, can we use a digital twin for process performance improvement? And second is, can the digital twin provide general solution to handle the heterogeneity in the equipment? And the third one, can we overcome the challenge of transferability to other locations? So this said, I'll pass the baton in the hand of Nader, who's going to go ahead and start talking to you about the digital twins.
Thank you. Hello, everyone. This is Nader. Here, I would like to talk briefly about the digital twin and the concepts and the challenges associated with it. And then I will talk about the development and design and implementation of our pilot, which serves as a physical twin for this project. Although there are several definitions of a digital twin, I like this short definition that says a digital twin is a virtual representation of an operating physical entity synchronized at a specific frequency and fidelity. So this physical virtual entity has to have several components in order to be considered as a digital twin. They include like an operating physical entity, and then a high fidelity simulator to simulate the main processes in the physical entity, and then sensors so we can get data throughout the physical system, and then the two-way communication between the physical and virtual entities, advanced data analysis in order to translate and basically curate the data between the physical and virtual entities, and obviously they have to provide the service. So if a digital twin is implemented in its full scale and full application, it can provide a variety of services, including the monitoring of the physical entity, optimizing it, and then calibrating the physical entity, and then also forecasting the behavior of the system, and then also evaluate the sensitivity analysis to the input parameters. And it also can serve as a safety feature. For example, it can shut down the system when a variable reaches a certain threshold. So in order to better understand what we have to consider and what challenges we are going to face in terms of implementation of the digital twin in the water industry, first we evaluated studies that focus on development of the digital twin in other industries to see what lessons we can learn from them. And then we reviewed over 100 papers and reports that they focus on development of digital twin in the water industry. As you can see on the right, I mean, you probably cannot see, it's very tiny, but we went through all of those studies, and then we figured what they focus on and what features of a physical twin of a digital twin they consider in their study. Although the majority of these studies, they haven't even come close to implementation of a full-scale digital twin in the water systems. Some of them, a few of them, they seem very promising, and the majority of those few are basically developed by major water design companies. So we are putting together also all of the findings from the review study through a comprehensive review paper. We're putting it together. And then so we defined the goal and objective of this particular project as development of a physical digital model to optimize the energy and cost associated with water treatment and water use processes, and to assess and address potential system anomalies. So for implementation of our physical twin, which is basically our pilot, we selected Orange County Water District, or OCWD. OCWD is one of the most advanced and largest water reclamation facilities in the world. You can see the process flow diagram for the facility in this slide. As you can see, they consist of like membrane microfiltration, ultrafiltration, and then cartridge filter, reverse osmosis, UV disinfection, and decarbonation. So although we had some limitation, and the plant is designed to basically produce 130 million gallons of water per day. So although we had some limitations in terms of space and budget and timing, we tried to design our pilot as close as possible to the main treatment processes as OCWD, and then keep our operating points as close as possible to the operating points of the facility. So you can see on the right the PNID for the pilot that we designed. It is designed to produce 11,000 gallons of water per day, and it consists of the major treatment processes at OCWD: ultrafiltration, UV disinfection, cartridge filter, reverse osmosis, and again UV disinfection at the end of the process. So we implemented our pilot at a RO building in Orange County Water District. As you can see, this is our pilot on the left. So we made all the connections. We are very, as Dr. Rosso mentioned, we are very grateful, very happy that the research team at OCWD, they are working and collaborating with us in this project. And so we implemented the pilot at Orange County Water District, and we made all the connections so we can run the pilot dynamically and continuously. And then we also equipped the pilot with a human machine interface. You can see on the right, you can see the screen is basically here on the pilot. So we can monitor it remotely, and we can manipulate the pilot remotely, and it provides an interface for the physical and virtual entities to communicate to each other, to talk to each other through this human machine interface. So in the past few months, we went through some modifications in the pilot. So as I mentioned, one of the goal of this study is to look at the energy consumption and to optimize the energy and cost. So we equipped the pilot. First of all, we basically loaded this pilot with sensors, so we can get data, real-time data throughout the system, continuously to monitor the operation of the system. And then we equipped it with power meters, so we can basically monitor the power consumption, the real-time power consumption of the pilot, one of the goals of the project. And then it gives us the true power at real time whenever we make any modifications, and then the net energy and the total power of the pilot. So the other modification that we recently made, as I mentioned, we have a UF system in the pilot. So although we are using the MF-UF effluent from Orange County Water District, we had some fouling issue with our UF. So we replaced our previous UF with two new UF modules, and these two UF modules are equipped with an automated backwash system. So OCWD, they backwash their UF system every 20-21 minutes, and then we programmed our UF so it also backwashes the UF module every 20 minutes. So and then also we as you can see the small portion here, so we modified our human machine interface also, so it reflects the automated backwash system, so we can also manipulate it, we can control it remotely and through and also through the digital twin. So for the simulator part, for the high fidelity simulator, we are using Sumo simulator developed by Dynamita team. The Dynamizer is the version of Sumo which is particularly developed for the water treatment and for digital twin purposes, which Oak Ridge National Lab team are going to talk about this in more details in the few next slides. So I'll hand it to Sally Ghanem from Oak Ridge National Lab.
Thank you, Nader. So we developed our digital twin with Sumo Simulator, which is a wastewater simulation software package that has a user-friendly graphic interface. Sumo was developed by a team of experts in Dinamita who has over 100 years of combined experience in modeling to provide water and wastewater treatment process simulation software. Dinamita's CEO, Dr. Emery Takash, is also a fellow of the UC Irvine Water Energy Nexus Center, and UC Irvine is also participating in the beta testing of the Sumo simulator. So what makes Sumo different from other simulators is not only being an open source model, but also being editable, because Sumo models are written in an Excel-based open process code called Sumo Slang, which can be easily modified if needed. In addition, the simulator features additional layers of energy and carbon footprint calculations based on the process model, and this capability can be used to assess the electricity demand and the carbon footprint of plant operation for a given period of time. The simulator that we use, the previous slide, Nader. So the simulator that we use, called Sumo Dynamizer, was built specifically for digital twins and can communicate with other programs such as Excel, Python, and MATLAB through its digital twin toolkit. And it can also perform sensitivity analysis and parameter optimization. Next slide, please. So we implemented the physical twin in Sumo Dynamizer, and the process model code is documented and provided in a Git repo. Next slide, please. We also modeled water district treatment train in Sumo Dynamizer and uploaded the documented source code to the same Git repo. And in Millen, we'll be talking about the two.
Good afternoon. So this slide gives kind of an overview of the way that we communicate with the pilot and the Sumo model and how we tie all these things together. So kind of the overall architecture. And I want to, I guess, draw attention to the fact that, as Diego said, this isn't really a one-off solution. What we're trying to build is an infrastructure for doing research. And so we have the physical pilot, and we can perform experiments on the physical pilot that we couldn't do on the full-scale system. We can take those measurements and draw those in and then use those to train the Sumo model. We can run the Sumo model from Python and run some optimizations. So we've built out a lot of this architecture and infrastructure that will allow us to continue to do lots of, I think, interesting experiments and try a bunch of different things out. If we can go to the next slide, Nader. So one of the first things that we need to do is we need to train the model to match the actual physical system, the pilot. And so we do that running a series of experiments on the pilot system itself. And then we run an optimization where, in this case, we're trying to match the power consumption from the model to the power consumption from the actual system. And as you can see on the right, we actually have a pretty good fit for the model to the actual measured power consumption. And go on to the next slide. So Sumo is kind of the modeling engine, but we're running everything through Python. And that allows us to call the model and get data back and then run various different optimizations, things like optimizing the specific energy consumption, and do things like calibrate the model, because we can change model parameters in Python, and those get pushed up to the model, and then we can get the results back and again do things like calibrate the model to the actual physical data. And just briefly, Brian will talk more about this in detail, but this is an initial optimization that we did, and so we're able to exploit energy prices and generate about a 5% lower specific energy consumption over a 24-hour period. But again, as Brian will talk about this in a little bit more detail.
All right. So kind of just to wrap up the last section, we're going to talk about the energy and cost assessment. So kind of the overall scope of this project is to map out what the design space of a plant like OCWD can be, right? And seeing how far you could push it in different directions with regards to, you know, how it operates, what are the limits on the processes. And we're doing all that testing on the pilot, right? But one of the things that we want to understand coming out of this project is what is the potential for the system to operate in ways that reduce energy consumption, reduce emissions, and or reduce cost, right? So we're leveraging the dynamic model of the OCWD facility and then also of the pilot to determine, you know, what are the energy and power dynamics associated with operating in response to electricity price variations. We're also interested in looking at what the response would be to emission signals, so that this sort of energy overlay will give operators just information of, if you do this, maybe you could save this % in cost, or if you take these set of decisions, you can maybe save, you know, this % in emissions. And it's up to the operator to decide whether that's worth it or not based on other priorities of the plant. But we want to be able to map that out, right? So these two tasks of the project, 12 and 13, is energy analysis and cost analysis of water reuse processes. So to do that, next slide. As Alex pointed out, first thing is we're applying this to the pilot because we have a lot of experimental data for the pilot, and that we can run experiments on the pilot in extreme conditions so that we can calibrate the model a lot more closely. And then we're also going to apply this framework to the model of the overall facility. So there's an optimization framework that was developed, as Alex talked about, and we have applied it to having a simulation of the pilot respond to a Southern California Edison electricity tariff. And we're also applying this to the full-scale facility. So first we had to calibrate the power consumption, as Alex showed. So that's just this graph. Go to the next slide. This is just an example of 1 week of what the electricity tariff looks like in Southern California Edison for summer and winter. I did have to aggregate these quite a bit, because if you go look at the tariffs, there's quite a few different ones, but this is just an example of how tariffs can differ between the summer and the winter. On-peak periods tend to be between 4 and 9, because that's when solar generation tends to start ramping down while the residential load peak starts to come up. And that means that Southern California Edison has to procure more expensive electricity from peaking power plants. So that's where they don't want you to use electricity, right? However, in the future, we could also apply not just SCE tariffs, but if there's potential for the plant to participate in the wholesale market or to provide other kinds of grid services, we can throw those signals in there as well. Next slide. And this is an example coming out of the optimization framework that was developed at ORNL and as applied to the pilot, looking at, you know, the recovery ratio. If you were to operate it steady state, which is how it operates today, it's flat, right, at a prescribed value. If you do allow it to vary, right, based upon the dynamic constraints in the modeling that we're doing, you could have it vary quite a bit. Now, practically, I don't know if plant operators would actually want to do this, but this is an example of how different the operation could be if you're going to respond to minimizing monetary cost. If you go to the next slide. Okay, so this comes with a disclaimer that we haven't fully optimized the optimization, right? There's still more to be done in terms of searching for solutions and playing with the cost function and the constraints. But for this initial example, we were able to get overall costs to be reduced by 5% with our modeling of the pilot. We're also going to look at whether the estimates of cost and energy savings from the pilot, how that translates to cost and energy savings of the full-scale facility. So we're going to be comparing those moving forward in the future. And then next slide. which I believe is the wrap up.
So, as I mentioned, we are using the Dynamizo by Dynamita team as our simulator. So we are basically simulating the main treatment processes in our pilot, and then also the main treatment processes at OCWD. So the water tap team also they are working on a steady state basically simulator. So we at some point in this project we started a PEG collaboration with the water tap team. And the goal is to compare the water tap team outcome and the Sumo or Dynamizo simulations at the steady state stages, and also compare the dynamic and steady state simulations with Sumo, and then also to determine where exactly the dynamic simulation would be needed in the water systems. So we are basically we have regular meetings with them. We exchange information regularly, and then we have given them access to the Sumo and Dynamizo, and then we are basically sharing all the data that we are getting from the pilot. So how it works briefly, basically we do a specific set points to the pilot, and then we get the outputs. We get the outputs out of the pilot. These are the real data. So we model with the same decision variables, the same input parameters in Dynamizo and the water tap team, and then we compare the steady state and dynamic simulations that we get out of those two to see how close they are to each other, and then how we can and then the water tap team, I know they are also working on making their model like more dynamic recently. So that's basically the goal of the collaboration. So I hand it to Chris.
Yeah, thank you, Nader. I have the pleasure to explain what we're going to do next. So we continue experimental work and data acquisition. We have a few experimental designs on the way, particularly to look at loading of the cartridge filter and membrane. However, if you feel like, look, there's the specific experiment that you should do and you may not have thought of, please let us know now that we have this set up. So we'll finalize the two-way connectivity to make sure we can control the system in real time remotely for defined test process conditions to essentially push the pilot to its limits. Next item, collect the data naturally and analyze it as we have. Then to tune the optimization framework, we'll finalize the decision variables, the objective function, as well as constraints. We'll test optimization as we started and showed today on basically in silico on the dynamic digital twin, then move to optimizing the physical twin. Next item, and ultimately apply optimization to dynamic model of the Orange County facility to see what optimization potential we have on the real plant relative to the pilot plant, and we'll explore the use of water tap for real-time optimization as well. To test cost and non-cost objective functions, we currently, as Brian has shown, focused on monetary cost based on utility tariffs. We can move towards wholesale prices, as mentioned. And we can also factor costs in that are non-monetary, such as carbon footprint or greenhouse gas emissions, all of which can be resolved in time. So the project provides crucial information on what we can do and what the challenges are with the use of digital twins at full scale. That's the first effort, as far as we understand, to have a full-scale digital twin system that can reduce cost in the water sector, not only monetary cost, but also energy, carbon footprint, and so forth. And the outcomes of this project will be critical to inform us, NAWI, as a community, as well as outside of the community, as to how and when we can optimize energy and cost for the water reuse system, as well as addressing potential anomalies as we optimize and move these systems to their boundary of operation. So finally, that should be a path forward to further research on implementation and use of digital twins in the water industry. Thank you. And that brings us to the Q&A, I think. If you can go back one slide now, that'd be great. So Diego said he would monitor us as well as the audience members for questions.
Yes, I promise to curate the chat and the Q&A. I have just one quick remark to make. You noticed, to make for the audience, you noticed that we presented here some examples of what we can do with this digital and physical twins. It takes, as you know from fieldwork, a long time to set up, and once it's set up, it's relatively fast to do the experiment and the simulations. And so now we are in the part where we have started doing the experiment and simulations, and we're going to be doing the ones that we envisioned, but also thanks to your feedback, we might polish them or improve them. So we welcome your feedback for sure. And there are a few questions in the chat. The first one, it was by Peter. I saw it earlier, and I think it's been answered, but I wanted to make sure that we cover it. So in addition to
I'm not sure it's been answered, Diego.
Oh, okay.
Yeah.
Well,
so the question I have is saving a small amount of money for utility. They are in the business of making water, and so cost savings are often not a dominant driver for operational decision making, and operators will tell you what they are willing and not willing to do. So I was wondering if, I know you haven't kind of measured any of these, but whether in your discussions with Orange County or whether in your discussions with the operator community, do you anticipate other benefits for having this kind of automated variable timing on this system? And it could go either way. For example, maybe the automated nature of it is easier to work into normal operator workflows, or maybe there's something about it doing too frequently that damages the equipment. And so another part of this question I have is, on a long-term average, are you backwashing as often as the regular periodic? And I forget, I apologize if you mentioned this, or on average, are you backwashing less frequently?
So I'll address the question at a high level, because this is a very important question. It's really central to the goal of the project. The question as we framed it, and I think it's just a different way to say what you're saying, is what is a reasonable ask to go to a utility and say, we have this different way to think about operation, we can model it. And what do you think you could implement or you'd be willing to implement? Of course, their role is to meet water quality, meaning the flow, and then secondary to that, all the other attributes. But we also have to remember that at the time when these processes were designed, the state of the art was like a set point, and then you operate and you meet your criteria. And a set point, in today's understanding of how we can use simulation and data, we can, without sounding pejorative, it will be like a legacy system. We can use multiple set points and achieve multiple goals, which is, the water quality as a constraint, okay, and also maybe saving some money in the process. Now, this is on the theoretical point of view, because we see it on a display and this looks wonderful. The practical thing is to match that with the physical limitation of the equipment and also the labor cost. Some of the things may require more maintenance than others, may require different type of labor pressure. So the final part of this research is to try to compare what is on the screen in terms of like an ideal world and what is in the physical limitation of the equipment, and also the non-equipment, non-technically related things. In certain areas, labor contracts are such that you can only have so many things that are different in other areas, and that has nothing to do with the process simulator. So that's the final part that really allows us to see a benefit to a particular utility, because ultimately only the utility knows what they can do and what they'll be willing to do. And working with them and always receiving this feedback, I think it's vital. And this is like a cautionary message for anybody who does any field work. Keep talking to the operators and engineers in the field and make them your new very best friends, because you learn so much more from them than what you came in thinking you knew. I would say, in California, carbon footprint is a very important attribute. And looking at minimizing the carbon footprint may be antithetical to minimizing the energy, because different hours of the day, there's a different carbon intensity for the same kilowatt hour. So if down the future, the utility sees the carbon footprint minimization is a priority, well, it's very easy to design an optimization scheme that meets that criterion, as a list of criteria, as a priority, okay, compared to others. Then again, it's important to respect and to value what the utility is willing and able to do. Did I answer your question?
Yeah, thank you. My second question, though, was on a long-term average, is the algorithm telling you to backwash about as frequently as the scheduled backwash, or do you find you are doing, on a long-term average, fewer backwashes?
I don't think we are at a long-term average just yet. I think our instruments are all still in the short term to establish the first phase. In the long term, that's an important question, because we want to also evaluate if there are any long-term repercussions of changing what is the state of the practice. So thank you. That's a good point, and we need to address that.
Good. Thank you.
There was, let me see, in the list here on the chat, I see that people are managing the Q&A already, so I don't think I need to go there, but I'll focus my attention to the chat here. I think the water quality in the effluent is a constraint, and the rest of the team can chime in and correct me if I'm wrong. And different time of use tariffs. Yeah, so the model, what Brian can chime in and really give you the entire answer, but we are surveying different time of use tariffs, not only one. And so depending on that, you enter it in the model, and the model calculates based on that. So that's an input based on the catalog of tariffs that Brian has compiled and curated.
Yeah. And I just want to add that, yeah, the tariffs are data sets that we can pull from different places, and they're exogenous to the optimization, right? So as far as the framework of the optimization is concerned, it's just a signal that it's going to that's going to incentivize it to optimize its operation to minimize the objective function, right? So that objective function can include different types of tariffs with different profiles, or it could even include things that are non-cost. So one thing that we wanted to look at is also if we put in a signal that represents emissions intensity, for example, what is that going to get you? So my understanding is that the optimization framework, it's sort of indifferent to what incentive signal you put into it. So that definitely gives us a room to look at different tariff structures.
And one thing we haven't really explicitly said, but it's obvious to us, and I want to make sure that it's clear to everyone, we don't aim at controlling a plant. We aim at giving information so those who have control authority can make more informed decisions, basically. So the person with a driver license still drives the car, but now has one more instrument, miles per gallon, not just the speedometer, the odometer, the RPM meters and such. So that's an important thing, because I think the utility eventually is the one who's going to take action. There is a question from Megan, speaking of utility. Can you clarify what was on the y-axis for variable operation? What is being changed by the operator to minimize energy costs? So in those plots there, I think there were the different process conditions for the RO. Is that correct? Is that the ones we displayed here?
Yeah, so the initial results were applying optimization to modeling of the pilot. And the two variables that they were using were the recovery ratio and the recirculation ratio in the pilot. Now, when we apply this to the full scale facility, we might choose different control variables, but the optimization framework has the ability to do that. And then Alex can add more detail if needed.
Yeah, so again, this is just a first pass at the optimization to really test our system to make sure that all the bits and pieces can talk to each other and get data transferred back and forth correctly. So this isn't an optimization that we would ever suggest that an operator does. It's more of just an example of, can we get all the pieces to talk to each other and work together. So we'll refine this optimization significantly in the future to be more practical.
Yeah, now that you saw that we can do it, now we can establish constraints that are more applicable to different scenarios and different facilities and different equipment. So the important thing is to establish the way to do it. So this is a method that we can apply and tailor to different scenarios and conditions. And thank you, Peter, for that great quote. Yes, it's not operator versus the machine. I think we will always need the operator. Somebody needs to take responsibility for running the plant.
I think also the operators are going to probably will help you reveal new value propositions with this sort of dynamic operation that we hadn't even conceived of. There could be these sneaky side things with respect to their workflows and how they do their job that this dramatically improves. Maybe the overall perception of value on the part of the operator community is going to be something very different than the cost and energy that we are optimizing against.
Yeah, and a typical scenario is that each one of the individual equipment unit or unit operations are optimized by the technology developer, the deliverer, and the operators get used to operating them in the optimal condition. But you know, a series of optimal condition may not be the optimal of the series. And that's something we're trying to compare here.
Yeah.
Okay,
Phyllis is asking these great questions about input water quality, and
I just appear on my screen right now. Input water quality.
Hi, Phyllis.
Maintenance. Will you be able to train the model on these factors? Well, you read our mind because we're having this discussion this week. Right now, we are having to establish the setup and the functionality of the pilot and the software. We are using what's available in that particular site within the plant, but also we are setting up an experimental plant where we can add to our feed tank different type of water quality. So we can use the filter water, but we can add to the filter water also maybe some backwash from the microfiltration. So we can basically reestablish a more realistic feed water only for our pilot. And that way we can also see if there is an anomaly in the water quality going in, how the pilot would look like. Those conditions that earlier Chris described as going beyond normal. It's very important because everything, I'm a professor and I teach how a process should work, but we should also focus on getting data on when the process does not work. And we cannot expect the main plant to actually do that. They want to stay as away as possible from conditions of anomalies. And so we want to do that on our pilot. We have the opportunity to do this in the pilot. And so measuring the current chemical constituents that you are getting now. So we have the ability to measure a number of things in real time, and also we have the ability to do the water quality measurements through graph samples and lab support here from our lab. But right now we're using the water from the plant, which is thoroughly monitored. So we can rely on their water quality measurements. I hope I answered that question, but if there are more details later on, I invite you to contact us for sure. All right, I don't think I missed anything. Have I missed any? We don't even understand the inside of the will be management information system. I agree with that. And earlier there was a question about Sumo. How do we set up the units? I think they've been answered in the Q&A, right? Can you explain?
Yeah, but we can dive in if you want.
Yeah, so I'll do this. Megan asked a question about the open source editable part. I'll explain it briefly. I'll let the people who really do the modeling on a daily basis explain it probably more in depth and better than me. So if you buy a simulator, it tends to be a compiled software. You buy it, you put in your setup, you run it, and it works. But you really cannot edit, say, how a process works. And so the nice thing about Sumo is that the solver, the part of the software that actually solves the equations, that's compiled and you don't need to touch them. Okay, that's a closed source. But what the open source part is the setup of the model. So you can click on any of these units, and then there's an overlay behind where you can change. For example, let's say that you have a new model was developed for one of these unit operations. Well, you can edit it and include it. And I'll give you an example that is not what's on the screen, but I work with them and we wrote a paper because we came up with a better model for gas transfer to be used in an activated sludge process. So we edited it, we entered a new equation, and that works much better than just using an input parameter or a scheduled parameter. Chris and the rest of the modeling team, would you like to add to what I said?
Sure. So just the strategy of the way this works is you have let's say a set of chemical reactions, and they end up in a so-called Couillard matrix. What that means is that each row in your Excel table will represent a reaction, and each column will be a constituent in the water. And then there's a final column at the end of this matrix that's basically the reaction rate. So if you want to change the process, it's very easy to change the chemistry or the chemical reactions that are occurring, or the separation phenomena that are occurring in a process unit by adding rows for additional, let's say, chemical reactions or separations, and adding columns for additional constituents in the water. So this is a very intuitive way to modify the processes as needed, and because it's you're interfacing with Excel, which most of us are probably familiar with, it's quite intuitive as well. So that's more or less how that works.
And I also would like to add that the data can be fed dynamically. So we have this tab inputs where we can feed the data, and we can have a dynamic data. It doesn't have to be like constant data. We can feed a dynamic data from the pilot to the digital twin and so on.
There's a question on the chat. I think Sally, you or Alex can address this. Are there challenges with Python integration with Sumo?
There are. They have a fairly good interface. It's not terribly hard to use, and they've got some pretty good example code. But essentially, it just the model is compiled into an executable, and the Sumo code, or the Python code, calls that executable. You can do things like monitor specific variables that you would like to get from the simulation, and you can also set and manipulate and change other variables in the simulation from Python. So that's kind of the workflow. Set a variable, run the simulation, get the results back, process.
And the comment in the chat by Ferry, who actually is one of the people who developed the software, he says you need someone who knows both Python and Sumo. And yeah, so what happened here is we organized a workshop, a training workshop to teach Sumo to our team, the broader team, and also we invited people from industry. So we tend to do this on a regular basis. And this is not the only software we use for education here, but we like to use it for research because it's editable.
So Diego, I think it's Emery who is in the chat.
Oh, it's Imre. Okay. Oh, yeah. Wonderful. Welcome, Imre. Yeah, a different name appeared there. Okay. I don't know how we're doing with time. Maybe somebody from the organization team can tell us if we have time for more questions. I don't remember.
We have till 11:30, but it seems like there is no more questions in the Q&A.
Okay, well, I don't see new questions in the Q&A and new questions in the chat.
Yeah, I think this was a great presentation, guys. And actually, I appreciate that you left a lot of time for good Q&A. And I can totally tell this is it's a nice diverse group of participants today. So as you know, we also record these, and we'll post this to the NAWI website, the NAWI HiveBright site. And I would just be happy to close everybody out by saying, you guys, we are so excited by this project. Look forward to seeing the progress you continue to make, and would love to hear about how your work is going with Orange County in general, and if what the operators tell you.